Thank you for the introduction, and I thank the organizers for this amazing conference. This is joint work with Roland Wirschema from the University of Waterloo and my colleagues Efekan Kokcu and Lex Kemper from NC State University. And, I'm a mathematician, my collaborators are physicists, so this talk will be very non-technical with lots of pictures that I borrowed from Roland. So it's more about the motivation. First of all, mathematicians care a lot about classifying stuff, and it all depends on the definition, of course. Here's an odd example. My favorite classification is Cartan's classification of compact simple Lie groups. And equivalently, it's the classification of simple Lie algebras over the complex numbers. They are organized by their Dynkin diagrams, and types A, B, C, D are the matrix algebras or matrix Lie groups SU, SO, and SP. And we have 5 exceptional ones. There are also a lot of classifications in physics. This is just one example. And actually, I don't know if it's related to anything that we're doing, but when you have different lists of objects, you can compare the two lists and see if some unexpected connection may pop up. Another use of classifications is that you can discover new examples and you can be certain that you covered everything. Also, you can test hypotheses or you can prove results just by doing it case by case. The main object of our study is dynamical Lie algebras, and this is actually the central object in Domenico D'Alessandro's book on quantum control and dynamics. If you have a Hamiltonian that is local, so it's a sum of terms that act on, each term acts on a small number of qubits, then you generate the Lie algebra from the terms of the Hamiltonian. Oops. So you take all possible commutators of the terms and you take all linear combinations. Or if you generate a Lie group by exponentiation, you get what's called the dynamical Lie group. Kind of a simple trivial example. If you start with the Pauli X and Y matrices, from their commutator you can get the Pauli Z, and that gives you the whole SU2. Here are more examples of dynamical Lie algebras. A local field, here we have terms that just act on a single qubit. Xi acts on, is Pauli X acting on the ith qubit. Here it's obvious that these terms commute and they just give you n copies of U1. If you had Xi, Yi, and Zi, the DLA would be n copies of SU2. Well, a popular example is the transverse field Ising model, where the terms are ZZ on neighboring qubits and the X's on the qubits. One can show that the DLA is SO2n. And another common example is the Heisenberg chain. Here we have XX terms, YY terms, and ZZ terms. And in fact, the DLA depends on whether n is even or odd. I'm just giving you the example of even n. In that case, the DLA is 4 copies of SU2 to the n minus 2. So these are block matrices. Now, with our definition, it's clear that we don't care about the coefficients in the Hamiltonians. We just care about the different terms. Now, let me explain a little bit to motivate the significance of the DLA, the dynamical Lie algebra. For example, in quantum control, you may have control over the coefficients, which means that you can generate all the possible OK, but you want to see if you can generate all unitaries, and in this case, the dynamics is fully controllable. And more or less equivalently, that means that the dynamical Lie group is the group SU2 to the n. And this, of course, we've all seen with universal sets of gates. When you have, here you have rotations that can depend on any angle. But if you care about the set of unitaries that you can generate from certain gates, then you want to know what the dynamical Lie group is. And actually, it's interesting to study this when it's not fully controllable. There is the notion of subspace controllable. And for quantum gates, for example, if we have certain stabilizers, then we may care about gates that commute with the stabilizers. Now, one place where this notion of DLA is important is for parameterized quantum circuits, where we have certain parameters theta, we have capital L layers, and one question is whether such a unitary can be, or rather this cost function can be efficiently simulated. And for example, this can be done in the case of free fermions for TFIM, transverse field Ising model, or when we have full permutation symmetry over the symmetric group Sn. And in fact, this cost function appears also in quantum machine learning. And yesterday, there was a talk by Enrico and Michael on barren plateaus. So that's another place where the DLA plays a significant role because of this formula now for the variance of the cost function. And yesterday, there was a similar formula for the variance of the gradients of the cost function. You can see it not only that you have the dimension of the DLA in the denominator, but also in the numerator. If you want more precise analysis, then you need to take the projection of your state onto the DLA and then take the purity. Another place where the DLA is important is the phenomenon of overparametrization. If you have a deep quantum circuit, then the more layers you add, the bigger depth, then it becomes easier to optimize, and it's conjectured, supported by numerics. Here the vertical line is the dimension of the DLA, that this depth is related to the dimension of the DLA. And one more place, a paper by my collaborator Roland. Again, if you're trying to calculate the gradients of some kind of unitary like that, then again, the computational complexity of calculating them is related to the dimension of the DLA. And so because of that, we want to find this DLA. What is it explicitly? But all the examples that people use all the time are just the two models, Ising and Heisenberg. And it seems that nobody knows any other examples other than fully controllable SU2 to the n. And so we set out to find more examples, but how do you find all examples? Well, you just classify everything. Of course, stated like that, the problem is too difficult. Because if you want to try to find all possible subalgebras of SU2 to the n, then there are just too many of them. There are old results by Dinkin about classifying maximal subalgebras. There are recent results by Zayer, Schurte, Herbruggen, where they classified all subalgebras of SU2 to the n up to n equal 15, and they have about 100 pages of tables. So it's not organized very well, and you don't see a pattern how to extend it to higher n. And in particular, we also want to know about the dimension of these dynamical Lie algebras. Is there anything between exponential and polynomial? Now, of course, in order to solve this, we need to put some restrictions. We can't, at least not yet, find all possible subalgebras. And so we're restricting to two local Hamiltonians. So the terms of our Hamiltonian are just products of different Paulis. They're allowed to be the identity. Not both of them, but one is allowed to be the identity. And we assume that it's translation invariant. So we put that on a 1D chain, and so whatever term, for example, let's say yy, you put on these 2 qubits, you put it on every other edge. And you could have other terms like iz and so on. We also considered periodic boundary conditions, and also the case of fully connected, when you consider all possible interactions. And actually now we have follow-up work, which is not finished yet, but we can solve it for an arbitrary interaction graph. And so the question is, with these assumptions, can we classify all such dynamical algebras? And this is really, oh, I'm going really fast. Okay. I can spend more time on this slide. So this is really the strategy, how we do it. As I said, the first step is to classify just on 2 qubits. So just try to find all subalgebras of SU4. And then once you have that, it tells you what you put on every edge. And then you put the same thing on every edge. And you just grow it. And again, in this work, we just do it on a chain. Now, a general result, which one can show in general, complete generality, is that any dynamical Lie algebra is reductive. It's a direct sum of simple ones and the center. But the problem is that any simple Lie algebra that has an n-dimensional representation is embedded in SUN. And so this is actually how Zayer and Schoetiger-Brungen approached it, but then it's impossible to go from there. But at least we know that we have a direct sum of things like SUN, SON, SPN, or exceptional Lie algebras, and the exceptional ones, in fact, don't appear in our case. So how do we find the summands? The first step is to find the stabilizer, to find all possible Pauli strings that commute with each of the generators of the DLA. And then they're going to commute with the whole DLA. That's kind of the key observation, which of course is not really new, because in the case of associative algebras, we have the von Neumann double commutant theorem that if you start with, let's say in the finite dimensional case that we have here, you start from an associative algebra, you take its commutant, everything that commutes with it, then you take the commutant of the commutant, and you'll get back your original algebra. In our case, we only get an upper bound. So we know that our DLA will be contained in the centralizer of this stabilizer. And if the components are all of the type SUN, in other words, if the system is subspace controllable, then that will be all. But we could have components that are smaller, like SO or SP. And how do you find the SO, for example, inside SU? Well, it's the fixed point of the involution sending a matrix A to minus A transpose. And then that determines skew-symmetric matrices. More generally, if we have an involution that fixes all the generators of the DLA, then because an involution takes a commutator to a commutator, it will fix all elements of the DLA. And so again, what we do is we find all involutions, and that gives us a smaller upper bound, and then it turns out that it's exact. We proved that by induction. Okay, so how do we find the subalgebras of SU4? First, we start with completely brute force. And here I should point out that, of course, SU4 is really small. So if you care about the subalgebras up to isomorphism, there are not too many of them. But in our case, we're interested up to symmetry, because you can have to a billion subalgebras, let's say XX, and when you grow that, even on the previous slide, if I put XX on the edge and I grow that to a bigger chain, it will remain a billion. But if I put an XY on an edge and then I grow it on the chain, I will have XY here, they don't commute anymore. And so I could have two one-dimensional billion subalgebras of SU4, but then in SU8, they're not the same anymore. So that's why we only care about symmetry, not up to isomorphism. And so we start with all possible just subsets of Pauli strings. Have 15 Pauli strings excluding identity tensor identity. This gives us 2 to the 15 minus 1 non-empty subsets. That's a big number. But then if we compute all the nested commutators, if we generate subalgebras from them, turns out there are only 146 subalgebras of SU4. And then by imposing the symmetries, which are just relabeling of the XYZ Paulis, or the flip of the string, like XY goes to YX, this number reduces to only 28. So that's more manageable. And then after that, for this 28, we just investigate how to grow them on a bigger chain. And it turns out that there are additional isomorphisms among them that give us a final answer, only 17 dynamical algebras. And that's our main result. Well, it's a big table. I promise that's non-technical, so that I don't expect you to read that. But I'd like to point out that in the paper we have more tables, and with the table, some tables give us explicitly all the generators, and then we identify them with some known models from physics, but some of them we couldn't identify with anything else, so they appear to be new. And also, one use is that now if you give me a set of generators, I know how to find the DLA. Well, if it's just too local, you look it up in the table, but more generally now we have methods for finding them, which I explained on the strategy slide before. So let me point out some special cases. Well, 6 of those algebras are fully controllable. They're the whole SU2 to the n. And again, for some of them, this is not obvious if you just look at the set of generators, but now we know how to do it, or you just look in the table and you see that it's true. Of course, we have the TFIM, which we know is realized in terms of free fermions. The DLA is just SON, or SO2n minus 1. We have the Heisenberg model, where now you can see the answer is different for n even and n odd. The reason for that is because the stabilizer is different. The stabilizer is actually always the same, just product of all x's, product of all y's or all z's, but in the even case, it's a billion. In the odd case, it's not a billion. That's why we get different answers. And we also get symplectic ones, which should be bosonic. And these two are pretty complicated, and they seem new, as I said. In particular, if you look at the dimensions, that gives a way to organize the Lie algebras, because it turns out that the dimensions are only linear, quadratic, or exponential. And the exponential ones grow as 4 to the n, like the whole SU2 to the n. And okay, to conclude, some implications and future directions. As I said already, we can actually put this on any interaction graph now. We know what the DLA will be, but of course it can be generalized further. It would be interesting to see if this helps for doing the dynamics more efficiently, and there are Lie algebraic methods for that, using Cartan decomposition, for example. So this could potentially be useful for circuit design, and the examples that I showed earlier with over-parameterization and barren plateaus, well, in our paper, we actually did more numerics with now some of the new examples that we had, which were not considered previously, and they still confirmed the conjectures. Okay, that's all. Thank you for your attention.
Thank you very much, Boško. Are there any questions? Yes, there are.
Yes, hi. So thanks a lot for this wonderful result. Yeah, I don't have any questions. I would like to still give 2 comments. One was about these results, like using Dinkin, that it's cumbersome and so on. I would say, first of all, that they did a good job, like Zayer and Herberg getting that compilation. Secondly, in an abstract level, you can use it very well. I would say, for example, we have a complete classification of if you have a free fermion or free boson algebra, then what if you add an additional term, any additional term, what do you get? Do you get universality or something smaller? That's done with such a type of Dinkin classification. Secondly, my second comment is about that's related also work I did with a, you said that there is no von Neumann type of commutant theorem here because two semi-simple Lie algebras could have the same commutant. That's true. However, they could have the same commutant, but if you take the tensor power of them, if it's semi-simple, and you look at the commutant of that, that will always be different. This we also looked at. That could be also useful too. That's I want to point out.
Yeah, thank you for these comments. And yes, I agree, of course.
Very cool result. Can you say a little bit more on why there's this gap between quadratic and 4 to the n, but nothing in between?
For now, it's a mystery to us. We don't really know.
Is that a conjecture or that theorem?
No, that's, well, this is for our DLAs. But also when we did that for other interaction graphs, we find the same thing. Although if you put different things on the edges, different interactions, for example, there is this Kitaev honeycomb model. In that case, you could get something sub-exponential, like quadratic times 2 to the n. So it may still be possible to get something in between, but we have to go out of the framework that we consider.
Thank you.
Yeah, thanks, Boško, for that talk. So one question I have is, so you mentioned once you know the classification of your Lie algebra, maybe you can exploit that to find a better basis or something for quantum dynamics. So what sorts of things would you look at? Let's say you've classified your Lie algebra. What would you do next?
Yeah, so at least this approach that uses the Cartan decomposition, the idea is that you start with some Hamiltonian, but then you want to conjugate it in such a way that it goes into the Cartan subalgebra where the terms become a billion and then you can just exponentiate it.
Okay, thanks.
More questions? I have a quick, very simple one, which is given that now you've done it for two local Hamiltonians and you said now you've got a recipe, you can technically go higher. For two local, we can look at your table for the recipe. Mm-hmm. Is there any way to automate this process, say, if, or do I think about doing it by hand every single time?
Yes, that's a good question. Some of this was done on a computer, the first steps that we did. But the final answer, we don't have an algorithm for that. So it would be good to automate that.
Thank you.
Maybe this is a question for you and maybe for Zoltan as well, which was, in the case where you're looking at, oh, this is shrinking. In the case where you go to, say, local fermionic systems instead, so you look at the algebra generated by Majoranas, mm-hmm. Has that been worked out? Is that what you were saying, Zoltan? Has that been worked out for these dynamical the algebras? When you have like a local fermionic algebra instead of a local Pauli algebra?
Yeah, there are papers on that, but I don't think there is a full classification.
Okay, of the same magnitude as this?
Not that I know of.
Okay.
Of course, that's something else we're thinking of looking at.
Of course, yeah.
Yeah.
Thanks.
If that's all the questions, then let's thank the speaker again. And who's next?